Okay, so these are basis functions for DCT. And if you look at these basis functions for very first coefficient, frequency is 0. And as we increase U, frequency goes on increasing. This is also true for discrete Fourier transform. In case of Fourier transform, when we take Fourier transform, we actually take weighted additions of sines and cosines, or your input signal is weighted by various frequencies of sines and cosines, and then we take their addition to get one frequency coefficient. And for even for DFT, very first coefficient has all same coefficient values, so it represents DC signal or a signal with zero frequency. And as we increase U value, we weight the input signal by higher and higher frequencies. So effectively, these transforms are useful to give you frequency spectrum or frequency details of input signal. Okay, so this is concept of basis functions related to DCT. Now, similarly, when we talk about images, like basis functions for images, we can extend this concept as basis images. Okay, so as shown here, these are the basis images for DCT. So for images, we have rows as well as columns. So we consider these DCT coefficients along horizontal direction as well as vertical direction. So here on this direction, this very first coefficient value is equivalent to 1, 1, 1, 1, that is zero frequency. Then we have A, B minus A. Now, if you look at A value is brighter than B value. This is your A, that is 1.306, and B is 0.54. Okay, so brightest value corresponds to A, that is 1.306. Then next brighter shade for 0.54. Then minus 0.54, that is minus B, is further less brighter shade, that is darker shade. And darkest shade is used to represent minus 1.306, that is minus A. So according to this variation, you can observe here, this is brightest shade, which corresponds to A, and this is darkest shade, which corresponds to minus A. So here you can observe this variation as A, B minus A. Then next row is 1 minus 1 minus 1, 1. So again, this 1 is equivalent to a bright shade and minus 1 is equivalent to a dark shade. 1 minus 1 minus 1, 1. And last row is B minus A minus B. So B minus A minus B is as shown here. And similar variation is considered along these rows. So here 1, 1, 1, 1, A, B minus A as shown here. Then 1 minus 1 minus 1, 1. So this darker region is enclosed between two horizontal bright strips. Then last is B minus A minus B. Okay. So if we consider 4 by 4 image, in that case, we will get 4 by 4, that is 16 basis images as shown here. And if you look at very first image, in very first image, all coefficient values are identical, that is 1, 1, 1, 1, 1, 1, 1, 1. So it represents average of your all pixel values, or it represents a signal with zero frequency, or we can call this as DC coefficient that we obtain by very first basis image. So we weight our input image by this basis image to get very first DCT coefficient. Okay, then this is your second image, third, fourth, and these are next rows. Now, if you scan in a zigzag fashion, see here in this direction, horizontal direction, we can say your frequency is increasing in horizontal direction. And when we go downwards, frequency is increasing in this vertical direction. So effectively, we can scan these images in a zigzag fashion. So this is first, second frequency, then next higher frequency, then this frequency, then this, then this. So we can scan these images in zigzag fashion. So when we scan these images in a zigzag fashion, we can get these basis images in increasing order of frequency. So your very first coefficient, which is complete white, represents DC coefficient, and the last coefficient, you can observe that there are many transitions, and this is nothing but your highest frequency coefficient. Okay, so this is concept of basis images with respect to DCT. Okay, now these are the basis functions for DCT when n is 8. So when we consider a signal length as 8, these are the basis functions. So very first coefficient is your DC coefficient. Then here you can observe frequency is slightly increased. Here it is doubled than previous. Then here it is further increased, and it goes on increasing till last coefficient value. So here we get highest frequency value. And this is first coefficient, basis function corresponding to very first coefficient, which has frequency 0. And corresponding to n image size n by n, we get these as basis images. Okay, so for n is equal to 8, means your image size is 8 by 8, we get these 64 basis images. Okay, so very first basis image has all coefficients of same value. So this is average, it represents 0 frequency, and as we move in a zigzag fashion, frequency goes on increasing. And if we look at very last coefficient, we get highest frequency component because of this particular basis image. Okay, so these are basis images for DCT with n is equal to 8. So hope this concept of basis images and basis functions is clear to all of you. Now let us solve one numerical based on DCT. So the first example is determine discrete cosine transform of following vector where fx is 200, 200. Okay, now tell me what is value of n for this particular example. Please type in the chat box. What is value of n? Yes, Sharan, n is 2 because vector length is 2. Now tell me if n is equal to 2 and if we want to determine DCT by matrix multiplication method, which matrix you are going to use? What is DCT coefficient matrix size when your fx has length 2? What is DCT coefficient matrix size? Yes, Sharan, your DCT coefficient matrix size is 2 by 2. So we have to use this particular coefficient matrix where if we take 1 by 2 common, root of 1 by 2, these terms are 1, 1, 1, minus 1. Now we can use our input signal and simply by matrix multiplication with this DCT coefficient matrix, we can get the DCT of given signal. Okay, so this is input signal 200, 200. Now we need to use this coefficient matrix where size is 2 by 2. Okay, and by using this matrix, by simple matrix multiplication, that is your signal x, which is represented here as a vector f0, f1, it has size 1 by 2. And here we need to consider transpose of this matrix because here we have considered this input signal as it is, that is 1 by 2. So we should consider here DCT transpose. So take transpose of this matrix, which is actually same as this matrix. Okay, so we can perform this multiplication f0, f1 multiplied by first column. So we get this value as first element, and f0, f1, this row multiplied by second column is as shown here. So effectively, result is 1 by root 2 into 200 plus 1 by root 2 into 200. This is your first DCT coefficient. And second DCT coefficient is 1 by root 2 into 200 minus 1 by root 2 into 200. Okay. So the final answer is as shown here, 282.84 and 0. Okay. Now on similar lines, I am giving you one more example and you have to solve this example. So second numerical on DCT, if your input signal is fx is equal to 8, 0. Now perform this computation. Again, you have to use DCT matrix of size 2 by 2. Simply multiply it with transpose of DCT coefficient matrix. So your if you can use this first equation fx into c transpose to determine DCT coefficients, or you can also use c into f of x transpose. That is, keep DCT coefficient matrix as it is and multiply it by transpose of fx, that is a column vector. Okay, so you will get your result DCT as column vector and not a row vector. That's the only difference. Okay. So now compute this and type your final answer in the chat box. For input signal 80, where this is fx, and as the size is n is equal to 2, we are considering 2 by 2 DCT coefficient matrix. So it is 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. So we multiply this row with first column. So 8 into 1 by root 2 plus 0. Then same row into second column, that is 8 into 1 by root 2 plus 0. So effectively answer is 4 root 2, 4 root 2. So the coefficient final answer is 5.6, 5.65. Okay. So both these coefficients are identical. Now from these two results, can we conclude something? When our input signal was 200, 200, what it indicates? Input signal, all input signal values are identical to each other. So this represents a DC signal, right? All the values are identical. In previous example, fx is equal to 200, 200. These two values are identical, means it is a DC signal. So for this particular example, you should get only one non-zero coefficient, that is your very first coefficient, because very first coefficient represents frequency 0 or it represents DC signal. So for the given input signal, as all the sample values are same, it means in your input signal there is only DC frequency, or it has frequency 0. The data represents 0 frequency, right? And there are no high frequency components. So for this particular example, you should get all high frequency coefficients as 0 value, because there is no high frequency existing in the input signal. You should get only one non-zero coefficient, which is very first coefficient. Okay, that is DC coefficient. And we got the same result. So here, very first coefficient, which represents DC signal, has value 282.84, and this is second coefficient is high frequency coefficient, and we are getting that value at 0. Okay, so from this result we can easily understand that in the input signal there are no high frequency components, because high frequency coefficients have 0 value. Okay. Similarly here, if you observe the input signal in the second example, first coefficient is 8 and next coefficient is 0. So it represents abrupt transition at the center, right? Abrupt transition from 8 to 0. So this is as if a step transition, and whenever there is step transition, it is associated with number of high frequency harmonics, or it represents high frequency components. So for this second example, if we look at DCT values, we are getting DCT values, non-zero value for first coefficient as well as second coefficient, and they are almost same. Okay, so it of course has some average value. Any signal 80, it has DC component, that is average value of this signal. And in addition to that, because of this abrupt transition, the high frequency components are existing, and that's why your second DCT coefficient is also non-zero. Okay, now one more example, solve this example. Determine discrete cosine transform of the signal fx given by 8888. Okay, and meanwhile, uh, type your attendance, last 5 digits of PRN number followed by your name. First type your attendance and then type answers for this last question. Okay, so here in this example, fx length is 4. So we need to use discrete cosine transform coefficient matrix of size 4 by 4, because here your x varies from 0 to 3 as well as u varies from 0 to 3. So we need to use DCT transform coefficient matrix with these particular values. Here fx length is 4, that is n is equal to 4. So we need to use this matrix as shown here, DCT matrix of size 4 by 4, and the values are as shown here. Now here A represents root 2 cos pi by 8, that is 1.306, and B represents root 2 cos 3 pi by 8, that is 0.541, and all these elements are multiplied by 1/2. This 1/2 is common to all these elements. So use this particular matrix 1/2 multiplied by 4 by 4 DCT matrix, and use it for matrix multiplication method in order to determine DCT of fx 8888. So after typing your attendance, now type answers to this question. Type DCT of this particular sequence 8888.